Okay, today our class will be shear stress, and we have two problems. I will do the first problem and give you some time to think about the second one. So for the first one, it is required to plot the shear stress distribution for the following beam cross section with V is the shear force equal to 15 kilonewton. Okay, so we have a beam cross section, I beam. This is the shape of the section, and we have a vertical force V, as you see here, is equal to 15 kilonewton. Okay, and what we need to do is to find the or below the shear stress distribution over the cross section. Okay, now I will open a file, a drawing file. So I will share this file. Okay, so today we will have to do the shear force. This is question 1. Sorry, my handwriting will be not good today because I don't have a pen. I'm using my mouse only today. So it will not be very good. So today we will do the shear stress distribution. The shear stress, the shear stress is represented by tau. Tau is the shear stress. So this is the shear stress tau. Tau equal to the shear force V times the moment of area Q divided by the inertia I times the thickness T. So this is our formula of shear stress, where tau is shear stresses and this is tau. V the best way is to remove this one. So we have tau is shear stress, V is shear force, and Q is the moment of area. Moment of area means the area A times a distance D. I is the second moment of inertia or moment of inertia we calculate last week. So this moment of inertia. And T is the section or the thickness of the section we study. T is section thickness of section. Okay, so this is the formula we will be using today. So it is important to know the terms of the formula. We have 5 terms, which is tau, V, Q, I, T. Okay, so we now can go to our problem. So what we have is a cross section here. Okay, this cross section is T section, sorry, I section. Okay. This is our cross section. So we have the dimension of this cross section is 60 millimeter, 12, and 12. And we have the dimension here are 20 millimeter, 80 millimeter, and 80 millimeter, and 20 millimeter, sorry. So the total dimension here for this one, the height, total height is 60 plus 24, so 84 millimeter. The total dimension for the horizontal direction is 120 millimeter. Okay, so this is our dimension, and we have applied force V in this direction. So if the requirement of this question is to find the shear stress distribution. So to know the shear stress, we need to calculate some parameters required for our calculation. So as we said in the previous slide or previous screen, we have tau shear stress equal to V is the shear force times Q is the moment of area at the section divided by I, the inertia, times T. Okay, what we know in this formula up to now, we know the shear force given to us, V, and we know the section thickness T. What else we need to know, or what is needed for us? Q and I. Q and I. I will start firstly with I. With I, we just calculate last semester, last class, in the previous class, and you today do the quiz about it. So if I ask you to calculate Ix for this section. For this section, it is a symmetric section. So if I draw the axis here, y-axis is a symmetric axis, x-axis is also a symmetric axis. So this is x-axis, and this is y-axis, is the vertical axis. Okay, and the centroid, this is our centroid. The centroid of this section is in the middle here. This is our centroid or CG. So do we need to calculate the centroid for this section? No, because it's already known in the middle of the cross section. So now if I ask you to calculate Ix, how can we calculate Ix? Firstly, we need to subdivide the section to 3 parts. This is area 1, this is area 2, and this is area 3. So the first area is green area, A1. And this one symmetric, so A2, A1 as well. And we have here in the middle A2. So we have 2A1 and A2. So Ix will be the summation of 2Ix1 plus Ix2. So for Ix, it will be 2 from Ix1. How can we calculate Ix1? This is area 1, so the centroid of area 1 will be somewhere here in the middle here. So this one will be, if I put it here, so in the middle of the 12, so 6 millimeter and 6 millimeter. So the inertia of A1 of the first area will be the parallel to X, which is 120 times the perpendicular to X, which is 12 cubed divided by 12, plus, because the centroid of area 1 is not coincides with the centroid of the total area, so we have the term A times D squared, or times the distance square. So we have the area, which is 120 times 12 multiplied by the distance squared. How much is the distance? The distance I'm talking about is the distance from the centroid of A1 to the centroid of the whole section, which is this distance. This distance, as you know, is half of this distance, half of the 60. So it is 30 millimeter. 30 millimeter. So this area, this distance will be 36, 30 and plus 6. So it will be 36 squared. This is the inertia for area 1, plus the inertia of area 2. How much is the inertia of area 2? Area 2, the centroid of area 2 is coincides with the centroid of the CG. So it will be, the inertia of A2 will be only the inertia about its own axis, which is parallel. What is the parallel coordinate parallel to X, which is 80, times the coordinate parallel to Y, which is 60 cubed divided by 12. So this is the inertia for area A2. So the total inertia for this cross section Ix will be, if you work out this, will be 120 times 12 cubed divided by 12 plus 120 times 6 squared times 2. This one will be 30.76 times 10 to the power 6. This is the first part, which is 2Ix1 plus 80 times 60 to the power 3 divided by 12 equal to 1.44 times 10 to the power 6. So the total inertia for this section will be 5.2 times 10 to the power 6 millimeter to the power 4. So this is the inertia of this cross section. Okay. Do you have any question about this inertia? This inertia, we have done this in the previous class, and we have done it today. So this is our first thing we have to do for this section. We know the inertia. Okay. So now we know what is the shear force, what is the inertia, what is the thickness. We still need to know how to find Q. Q, just extend this. The definition of Q is the moment of area. Okay, what this mean? Means that Q at any section equal to the area times the distance from the CG of this area to the section. As example, if I want to calculate Q at CG or at section at axis XX, if I want to calculate Q at this point 1, so Q at point 1 will be, let's say Q1 here, and the will be the area above point 1 times D1. Okay, so this is the definition of Q, and we will use this while we are doing the example. So do you have any question about I or Q? Do you have any question about I or Q? Because Q is different depending on the point. So we don't have only one Q. We have to calculate Q for each section. Okay. So for now, to continue in this example, I will close this screen and start a new screen. So we have tau again equal to V times Q divided by I times T. What we know here is that V equal to 15 kilonewton given in the example. We have Ix, we just calculate Ix equal to 5.2 times 10 to the power 6 millimeter to the power 4. This is what we have done till now. The next step is how to calculate the shear stress distribution. If we draw the section again, I will draw the section again here. So this is our section. Okay, and the dimension of this section are 20 millimeter, 80 millimeter, 20 millimeter, and here we have 12 millimeter, 12 millimeter, and 60 millimeter. Okay, and this is our axis, y-axis, and this is x-axis. This is the centroid, CG. Okay, to draw the shear stress distribution, we need to mark or create a cuts that we need to calculate the shear stress at. So the cuts will be horizontal cuts because the shear force is vertical. So this is our shear force. So we need to calculate the shear stress at different sections. The first section at the top of the cross section here at the beginning of the section. This is our first section, section 1. So we have a section at the beginning and at the end of the cross section. This two cuts, but I will change the number here. So we have cut at the top and cut at the bottom here and here. This is our first two cut. Again, we have our second cut should be before and after any change of the shape of the cross section. So here at this point, at this level, the cross section was 120 in width and then become 80. So here we have two cut at this point. We have cut here and cut here. So this is section 2 and section 3. So here and here. Cut 2 before the in the wide width and cut 3 in the narrow width. Okay, and we need to have a cut at the centroid or at the CG of the section. So this is our section 4, and then we have to mirror the section. So here before the increased thickness 5, and here after the increased thickness 6. Okay, then what else we have? We have the last section, which is section 7 at the end here. So this is section 7. So how many sections we have to draw the shear stress diagram? 7. We have at the beginning of the section, at the top of the section, and before and after any change in the shape, and at the maximum, and at the centroid, and finally at the end. Okay. Do you have any question about the section? So we have to calculate 7 taus to finish to finalize the stress distribution. Okay. So if I ask you to calculate tau at section 1, so we will calculate first and then we draw. The first step is to calculate tau at section 1. For any section of this section, V and the Q, V and I are constant. So what is changing for the section Q and T? So for each section from the 7th section, we have different Qs and different T. For section 1, how much V? V is equal to 15 kilonewton. So I will convert it to be Newton. So 15 times 10 to the power 3 to convert it to Newton. So to convert it to Newton here will be 15 times 10 to the power 3 Newton. This is the first step. Then I, given we calculate I from the previous step, 5.2 times 10 to the power 6. This is the two constant in all sections. Times and times. How much is the thickness of the section here? The thickness here at section 1 is the whole or the wide section, which is 120 millimeter. So T here is 120. And how much Q? Q is the area, Q1. I will calculate Q1 here. Q1 equal to area above the section, above section 1, times the distance to the CG. How much is the area? This area is 0 because no area above section 1. This is section 1 here. So the area above 1 is 0. So how much Q1? Q1 equal to 0. So how much the stress at 1? The stress at 1 will be 0. So for your information, the stress at the beginning and end of the beam will be 0. Why will be 0? Because there is no area above the section. Okay? So this is for tau 1. For tau 2, I will remove this part. Tau 2, how can we calculate tau 2? What is the constant things, constant parameter here? 15.15 times 10 to the power 3. V is constant. And the inertia for this section is 5.2 times 10 to the power 6. So Q and I are, sorry, V and I are constant for the whole section. Times the thickness and times the Q, the moment of area. For the thickness, how much is thickness here? At section 2. At section 2, this is section 2 here. So the thickness at section 2 is still 120. And for Q, how much Q? Q2. Q at section 2. How much Q at section 2? If I take this area outside here, so this is area 2, area at 2, and we are calculating here at this section, section 2. Where is the centroid of this area? This is the centroid of this area. What is the distance between the centroid and the section we are calculating at? If this 12 millimeter, so this distance should be 6. So do you know how much Q2? Q2 will be the area. The area is 120 times 12. So the area 120 times 12. This is the area. Times is the distance from the centroid of the area to section 2, which is 6 millimeters. So Q finally will be 120 times 12 times 6 will be 8,640 millimeter to the power 3. So 8,640. The unit is in millimeter to the power 3 because it is the product of area in millimeter squared times distance, which is in millimeter. Okay, so from this formula we can find that the stress at section 2 is 0.27. So the final stress here will be 0.207 Newton per millimeter squared. So this is the stress here. Okay. Sorry guys, there is a small mistake here. Okay, I just will change this. Q2 is wrong. Q2 is calculated up to the centroid of the whole section. Okay, so just delete this one. We'll repeat this one again. So Q is the moment of area from the centroid of the total section. So Q here is not this number. This value is wrong here. So if we take it out like this, so we need to know where is the centroid of the whole section, which is here, somewhere here. This is the x-axis of the whole section. Okay, this is our x-axis. So we need to calculate up to the centroid. So this one 6 millimeter and this one is 30 millimeter. So the total distance here is how much? 36. So it should be 36 millimeter, and we put 36 here. So this will give us Q2 will be 51,840 millimeter to the power 3. Okay, if we put this value here, so 51,840, the value of the shear stress at this point will be 15 times 3 times 51,840 will be, the value here will be 1.246 Newton per millimeter square. Okay, sorry for this error. So now we find the stress at section 1 and section 2. So now we have to calculate at section 3. Now at section 3, if you have a look at section 3, again, the force or the shear force is still same, 15 times 10 to the power 3. The inertia still same, 5.2 times 10 to the power 6. So what is the difference here? The difference again is the thickness T and the moment of area Q. So if we have a look here, the thickness at section 3, how much the thickness at section 3? This is the section, the thickness here is, if you have a look here, how much? It is the narrow section, which is 80 millimeter. So instead of 120 in section 2, it become 80 in section 3. How about the moment of area Q3? Q3 here, if we have a look at section 3, section 3 is here. So the area above section 3 is same to the area above section 2. This means that Q3 equal to Q2 equal to 51,840 millimeter to the power 3. So for your information, you have to know that at any change of shape of the cross section, the moment of area will be same because the area, they are at same line. So the area above this section is same. So the area the moment of area at section 3 equal to the moment of area at section 2 and equal to 51,840. So 51,840 millimeter. So if we substitute in this equation, we can find that the stress at 3 is 1.869 Newton per square meter. This is the stress at section 3, and it is a little bit greater than section 2. Why section 3 has greater stress than section 2? Because the comparison here depending on the thickness T. So section 3 has less thickness, so that's why the stress is increased at section 3. Okay. The last section we have on the top part is section 4. If I ask you to calculate the area at section 4, so here now it's time for tau 4. Tau 4 equal to tau max. So you have to know this information as well, that the maximum stress here is at centroid. So you have to know that the maximum shear stress will be at the section of the centroid. So because section 4 passing through the centroid, this cause that the maximum stress will be at section 4. Why the maximum stress at CG? If you have a look to the equation again, we have V times Q divided by I multiplied by T. So for any section, we have V and I constant as we mentioned. So we have two parameters that control the maximum stress, Q and T. Okay, for this section, Q max, or for any section, mostly Q max at centroid, because Q max equal to area times distance, and the maximum area will be at the centroid, because if you have a look here, the maximum area or the maximum expected area for this section will be above the centroid. So this is the maximum area we can get. That's why Q max or tau max will be at the centroid at section 4. So if we substitute in this equation, we know that Q tau max equal to V, which is 15 times 3, 10 to the power 3, divided by the inertia constant 5.2 times 10 to the power 6. Okay. What is the thickness of the section here? The thickness here is this distance, which is 80 millimeter. So the thickness is still 80 millimeter. How much is Q for this section? Q at section 4 will be the area above the section. How much is the area above the section? We have two areas above the section, area 1 and area 2. So we have two areas now, so we need to sum them together. So area 1 will be, so Q4 will be area 1, 120 times 12 times the distance. How much is the distance? 36. So from the centroid here to here to the CG here, it is 36. And from the centroid here to here, how much? This one is 30. So this one will be 15. So we have, this is the first area, area 1, plus the second area, which is 80 times 15. This is the area times the distance. The distance is 15. So we get that the moment of area Q sorry, this area is 30. The area is 80 by 30. Sorry, guys. Okay. So 80 by 30. This will give us the moment of area equal to 87,840 millimeter to the power 3. So if we put this value here, we have 87, 84, 0. So we can find that tau max or tau 4 will be 3.16 Newton per millimeter square. So this is the values we have got till now up to the centroid. Okay, now we can start drawing. I will show you how to draw now. If this is our section, so we have first to draw a datum parallel to the force. So we have to draw a datum parallel to the force here, and with the length of with the height of the section. So this is our datum. Then we have some guidelines. We will have some guidelines here. Guidelines will be at the section we calculate at. So we have section 1, section 2, and section at max, and section 5 and 6, and section 7. Okay, we don't have to extend like this. I will delete this part. Okay. So here I will draw the shear stress distribution using the calculation we have done. Okay, so this is our shear stress distribution. Okay, so this is our shear stress distribution, and we need to plot the values we got. We got a value at section 1 equal to 0. So we have at section 1 here, value is 0. The value at section 2 is, as you see here, this is the value at section 2, 1246. So I will put the value of section 2 here. 1, 2, 4. I'll put it here. 1.246. Okay. How can we connect section 1 and section 2? The shear stress is a parabolic relationship or second degree relationship. So we will connect these 2 points together with a curve. So I will connect them with a curve like that. Okay, so from section 1, this section 1 to section 2, we connect them with a curve. Then at section 3, we have to put section 3 at this line as well. So section 3, the stress was 1.86, 1.869. So 1.869, and I will put it here, somewhere here. This is the value here. 1.869. Okay. So how can we connect them together? Because they are on same line, so I will connect them with a straight line like that. Okay. So this is section 2 and this section 3. How much is the shear stress at section 4? The value at section 4 is 3.16. So I will put it somewhere here. Here is the value of the maximum stress, tau max is 3.16. How we connect section 4 and section 3, the value 3.16 and the value 1.86. Same thing, because the relation is parabolic or second degree relationship. So I will connect it with a curve like this, or can try this curve. Okay. So again here. This is the curve from section 3 to 4. We have a curve because the shear stress relationship is parabolic or second degree relationship. So this is the top half. What do you think about the bottom half? As section X is a symmetric section. Section X is symmetric because so the first half or the top half is similar to the bottom half like this. So we don't have to repeat the calculation. What we need to do only is to mirror the drawing. So if we mirror the drawing, here will be the value here, same value, and the value here will be same value, and the value here is 0. And we can connect the bottom half like this. So I will connect with different color. If we connect these two together, okay, the value here is same value at the top, 1.869. And we should connect this two value with a line. So this is a line we have. Okay. This value is same value to the top part. The value here is 1.246. And the value here is 0. So we connect these two together with a curve as well. So from here to here, we have a curve like this. Okay. So now we have finished the stress distribution, shear stress distribution. We have to calculate at section 1, 2, 3, 4, and then mirror the calculation to the bottom half. Okay, so this is the final results. And do you have any question for this one? So you have to only know the formula and how to find the parameter of the formula, and that's it. After you calculate the stresses, you have to plot it like this, and you can connect. You have to connect the result, the points of or the values of the shear stress at each section with a curve. Okay, instead, except for the sections like section 2 and 3, because they are on same line, so you connect them with a straight line. Okay, do you have any question for this one? Do you have any question? All good? Okay, I will show you now. I will stop sharing now and show you the result. Can you see the screen now? This is the results, the final result. As you see here, this is the stress distribution for the cross section. You have a curve, you have to connect with a curve like that. Okay? Okay. Do you have any question for today? Okay, thank you guys. If you want, you can try the second question, and if you have any problem, let me know by email or next week. Okay, and next week will be practical, so we will have some beam testing deflection. So next week will be practical section, practical class or practical session, not a tutorial class. Okay, thank you guys for attending today, and see you next week. Good luck.